Alright, in this session we're going to talk a little bit about circles and then connect that back to some of the special triangles that we talked about and something that's called the unit circle. But first, we'll call this Circles in Trigonometry with the subtitle Unit Circle. So first, to talk a little bit about a circle in general, and I'm just going to show a circle centered at the origin of a Cartesian grid. Oh, that's a lovely circle that I've just drawn there. Terrible. So if I pick some point on the circle, out here say, it would be at a coordinate x and y. Now if I went a little further and drew a triangle in here, based on this, what can I say? I can say this side of my triangle is x, and this side of my triangle would be y. And I'll call this the radius. But this is also three sides of a right angle triangle. On this circle with radius r. So what's my relationship between x, y, and r? Well, I think by Pythagoras, x squared plus y squared equals r squared. And this is also referred to as general equation of a circle with radius r centered at the origin. Any point that's on my circle, the x and y coordinates of that point have to satisfy this equation. So, a couple of examples of working with this. Example 1, off of page 82, asks you to give the equation of a circle with a center at the origin and a radius of 2. Well, for any circle, x squared plus y squared would have to equal r squared. So in this particular case, x squared plus y squared would equal 2 squared, or 4. And that's it. Now, what this can allow us to do is to talk a little bit more detail about any point that happens to be on a circle. I think I can fit example 2 in down here. It's example 2 on page 83. And it defines something that we call a unit circle. Now, a unit circle is a circle with a radius of 1 unit. So the equation for a unit circle would be x squared plus y squared equals 1. And in example 2, we're asked to find a few coordinates on the unit circle. Part A, we're asked to find all points on unit circle where the x coordinate is 2/3. It's 2/3. Well, I know that x squared plus y squared has to equal 1, which means I know that 2/3 squared plus y squared has to equal 1. 2/3 squared is 4/9. I subtract 4/9 from each side, and I get y squared equals 5/9, or y equals plus or minus root 5/3. What would that look like on my unit circle? If this is out at 1, since it's a unit circle, 2/3 would be around here. So this point would be 2/3 and root 5/3. Apologize for this getting a little cramped. My other point would be 2/3 and negative root 5/3. Didn't quite have enough room for all, so I'll do part B on the second page. And I do want to say, where we're calling this the equation of a circle, notice we're not referring to it as a function. Because in a function, every x value should only have one y value attached to it. But here, as we can see, we've got an x value with two different y values attached to it. That's because where this is an equation that does describe a circle, it is not a function. So this is now example 2b, or not 2b? No, 2b. From page what was that again? 83. So same setup. Find all points with y coordinate -1/√2. So I'm not really happy with them, leaving it as a radical on the bottom. And in quadrant 3. Now this restriction to put it in quadrant 3 is actually going to cut us down to just 1 point instead of 2. First, I'm going to rationalize the denominator on this 1/√2. I get -√2/2. Then it has to satisfy my general equation for the unit circle. So my y coordinate is -√2/2, which I square. The negative is going to go away when I square it. √2 squared is 2. 2 squared is 4. This will result in x squared being equal to 1/2. Actually, I'm going to leave it as 2/4, which means x equals plus or minus √2/2. However, knowing that I want to end up in quadrant 3, with a y value of -√2/2, somewhere around here, to be in quadrant 3, I'll have to come over this way, which means my coordinate point is -√2/2, -√2/2. Crowded a little bit on the insert camera there, but there it is. So, knowing the general equation for a circle, you can work out different coordinates with a little bit of information. Now I want to talk a little bit about how the unit circle connects us back to trigonometry, and it's going to do it through those special triangles. So we'll call this the unit circle and trigonometry. And to recall a couple of things, we're going to remember the special triangles that we had talked about before. Turns out, if I've got a right isosceles triangle with a hypotenuse of 1, the two sides work out to be √2/2 and √2/2. And that's with 45-degree angles on the inside. We also had the case of a 30, 60, 90 triangle with a hypotenuse of 1, where our two sides worked out to be 1/2 and √3/2. And this angle was 30 degrees, and this angle was 60 degrees. Now, if we go and look at a unit circle, and it's a unit circle that we're going to draw fairly large, and quite off-center apparently, good for me. So these points out here would be the points 1 and 0, 0 and 1, -1 and 0, and 0, -1. Now let's think about a few of these special triangles crammed into this circle. If I come up 30 degrees, and since it's a unit circle, I know the radius is 1, that means I can show that this point is going to be at an x value of √3/2 and a y value of 1/2. But what else do I know about that? From this triangle, I know that the cosine of 30 degrees is equal to √3/2, and the sine of 30 degrees is equal to 1/2. And those are the two coordinates here on this point in the unit circle. If I come up to a 45-degree angle, then I've got my other special triangle, which would have coordinates √2/2 and √2/2. But I also know from this triangle that the cosine of 45 degrees should equal √2/2, and the sine of 45 degrees should equal √2/2. The same two coordinates there. In fact, that's always going to be the case if I can get a special triangle in here. My x coordinate will be this side of the triangle, but it'll also be the cosine of the angle. Similarly, my sine value will always be this side of the triangle, which will be the y coordinate of this point. If I drew a 60-degree in here, this is getting a little messy. I'll try to cram one more. Then this is just this triangle again, but flipped around into a different orientation. The small side would be 1/2, and the long side would be √3/2. But if I think about this triangle, the cosine of 60 degrees should be my adjacent side of 1/2, and the sine of 60 degrees should be my opposite side of √3/2. I should stress in each case that it'd be divided by 1 because that's my hypotenuse. So what we can see here is that for all these points on the unit circle, the x-coordinate gives you the cosine of the angle that's inscribed here, and the y-coordinate gives you the sine value of the angle that's inscribed here. Moreover, if I carry this further, let's say I draw my 30, 60, 90 up here. Not perfectly to scale, of course. So if this is 60 degrees, that means this is 30, and my angle in standard notation would be 120 degrees. My x and y coordinates would be the same side lengths from here. This would be my short side, this would be my long side, but now my x value is negative. What does that tell me? It tells me the cosine of 120 degrees is -1/2, and the sine of 120 degrees is √3/2. And as you carry along, you can actually get a number of exact values for sine and cosine just by using these two triangles. I'm going to go onto a new page and show you a bigger version of this. See how this turns out. I should go down here, I guess. This is somewhat circular-ish. Oh, for pity's sake. It's enough to get the point, I guess. Now, a bit of notation on this. although this is kind of a sad unit circle. P theta represents the point on a circle at the end of a terminal arm describing angle theta. So for instance, this point here I could refer to as P0, and it would have coordinates 0 and 1. If I went up a little bit, and I'm just going to draw the triangle for the first case, if that's 30 degrees, then this is P 30 degrees, and it would be equal to root 3 over 2 and 1/2. I'm not going to try to draw in all the triangles, but you'll start to see I'm following a pattern as I do this. Oh, just realized I did P0 wrong. It's 1 and 0. That's disturbing. Keep coming across. P at 120 degrees would be negative 1/2 and root 3 over 2. If I keep following the triangles along, P at 135 degrees would be negative root 2 over 2 and root 2 over 2. P at 150 degrees, that point would be negative root 3 over 2 and 1/2. At 180, that point is negative 1 and 0. I keep going. It's getting awkward now. P at 210 degrees would be negative root 3 over 2 and negative 1/2. P at 225 would be negative root 2 over 2, negative root 2 over 2. Right down here. P at 240 degrees would be negative root 3 over 2, negative 1/2, and negative root 3 over 2. P at 270 would be 0 and negative 1. P at 300 would be 1/2 and negative root 3 over 2. P at 315 degrees would be root 2 over 2 and negative root 2 over 2. And finally, for the circle, P at 330 degrees would be root 3 over 2 and negative 1/2. And if I wanted further angles, I mean, this would be P at 360, this would be P at 390 as well, P at 405 degrees, and so on, if I keep cycling around. But what I've also got on this is the measure for cosine and sine for all of these angles that I listed here. I want to know what the cosine of 150 degrees is. I think about where this point would be. Cosine of 150 degrees would be negative root 3 over 2. I want to know the sine of 300 degrees. I'll choose 330 degrees. I get to 330 degrees. Think about where this point is. Sine would be my y value, or negative 1/2. So for any point on the unit circle, I'm going to write this in the center, for any point p theta on the unit circle, the coordinates are cos theta and sine theta. So you could even use that to talk about points that aren't necessarily at the end of one of these special triangles. For instance, if I quickly go back to that last example, this will work. Whatever angle is traced out here, I know the cosine of that angle is negative root 2 over 2, and the sine of that angle is negative root 2 over 2. In fact, that's nicely on my unit circle, so I can also figure out that that is 225 degrees. In the first example, this is not one of my special triangles. Without knowing the angle, I could say the cosine of that angle is 2/3, and the sine of it is root 5 over 3. If my angle happened to be down here, all the way around, the cosine of that angle is 2/3, and the sine of that angle is negative root 5 over 3. So that gives us a way to connect the circle back to our base ratios in trigonometry. Now I just did these in degrees. Obviously you could do the same thing in radians and have each of these stated in radian measure instead of in degree measure. Okay, that's about all that I have to say about that for now. Thanks for listening, everybody.